Hello students, welcome to EPG Pathshala. I am Tonusri Shahadas Gupta, Professor and Associate Dean in S.N. Bose National Center for Basic Sciences in Kolkata. I belong to the Department of Condensed Matter Physics and Material Science. I am also the coordinator of the thematic unit of excellence on computational material science set up within S.N. Bose Center. In this lecture, we will continue with the modern density functional theory as given by Weinberg, Kohn, and Sham. In particular, we will focus on the practical implementation of the density functional theory. While the density functional theory is exact in principle, the crux of the problem lies in the fact that exact expression for the exchange correlation energy and potential are not known. Hence, these quantities are to be approximated. Various different approximations used by the practitioners will be discussed. In particular, the most popular approximation, namely the local density approximation, which is abbreviated as LDA, will be discussed. This refers to a class of approximation to the exchange correlation energy functional in the density functional theory that depend solely upon the value of the electronic density at each point in space and not, for example, on the derivative of the density or the Kohn-Sham orbitals. The overwhelmingly successful local density approximation are those that have been derived from the homogeneous electron gas model. In this regard, LDA is generally synonymous with the functionals based on the homogeneous electron gas approximation, which are then applied to the realistic systems. While the success of local density approximation or LDA is apparently rather surprising, as it is based on the solution of the homogeneous electron gas problem, we will argue that the reason lies in the fact that exchange correlation energy functional depends on the integral which describes the inverse extension of the exchange correlation whole. If this inverse extension is approximated correctly, the LDA is then expected to work well. As clearly understood, this is a much easy condition to meet than the requirement of the slowly varying density, as one would assume as the criteria for the local density approximation to work in a strict sense. It was mentioned by Kohn and Sham in the 1965 paper that we don't expect an accurate description of chemical bonding. However, in reality, LDA describes the covalent bonds, metallic bonds, ionic bonds rather well, though there is a tendency to overbind slightly. We'll also discuss more sophisticated approximations to the exchange correlation energy, namely the generalized gradient approximation, that is, addition to the local density employs the gradients of the density. Local density approximations, as well as the generalized gradient approximation, which popularly is known as GGA, are employed extensively by solid-state physics in ab initio DFT studies to interpret electronic and magnetic interactions. These approaches are also known as first principle calculation, as it is free of any adjustable parameter. Only information required to carry out the calculation are the structure and chemical composition. Cost of calculations are limited by the system size and the simulation time. Finally, we'll discuss why density functional theory, which is a single electron mean field theory in the same spirit as Hartree and Hartree-Fock, is so successful. We'll hint to few plausible reasons that include use of variational principle, the exclusion principle, and the screening effect. With this brief introduction, we now move on to the details of the methods and the approximations. The objectives of today's lecture are the following. First, we'll start by recapitulating the Weinberg-Kohn-Sham theory. We'll then discuss the crux of the problem, which is the determination of exchange correlation functional. We'll then discuss the approximations to exchange correlation functional. In particular, we'll discuss the following topics: the local density approximation, which goes with the name as LDA in its various flavors. We'll discuss why LDA works in the way it works. They will then discuss another approximation, namely the generalized gradient approximation to the exchange correlation functional. Finally, we'll discuss why density functional theory, which is a single electron theory, is successful. Weinberg-Kohn-Sham theory can be summarized in the following way. Firstly, the ground state energy E of a many electron system in presence of an external potential VR is a functional of density as is shown here, where F is an universal function which is function of density only and does not depend on VR as is shown here. The term F is a functional of density which is a function of the space and position coordinate R. Secondly, energy is minimized by the ground state density. This leads to the Kohn-Sham equation, which are set of n nonlinear integro-differential equations as given in the following, given by minus half del square plus V effective times psi equal to epsilon I psi I, where V effective is given by this following form, which is the contribution of the potential from the ion or nucleus, the Hartree contribution, and finally the exchange correlation part. The exchange energy functional, which is shown here, when added to the total energy functional, is given by this following expression, which is summation over I epsilon I minus integral of rho r prime divided by r minus r prime dr prime plus the exchange correlation energy EXC minus integral of dr rho r delta E exchange divided by delta rho r. Note this exchange correlation potential given by Vxc is given by the variation of this exchange correlation energy with respect to the density. The exchange correlation energy Exc, which depends on the density of course, is given by the difference between VEE and the E coulomb together with that of the difference between the interacting and non-interacting kinetic energy. While this theory is exact in principle, the crux of the problem lies in the fact that exact expression for exchange correlation energy and potential are not known. Hence, these quantities are to be approximated. Let us consider the simplest situation in which the true electronic system is endowed with only one aspect of the electron interaction. Of course, that belong beyond the Coulomb repulsion or the Hartree term, that is the exchange property. As we saw in the case of the Hartree-Fock approximation, which takes into account exchange explicitly, the contribution of exchange to the total energy of the uniform system is given by this following expression, where n is the total number of electrons obtained by integrating the charge density over the space coordinate. Let us generalize this for the situation where the density is not uniform, but we assume that still the same expression holds good. Therefore, one can write Ex, which is a functional of density, equal to integral of epsilon x, which is a functional of density, times density integrated over dr. Using the form of the Fermi wave vector, which is given by Kf, which is 3 pi square times density to the power 1/3, one gets the expression for epsilon x here in this above integral given by this following expression. This allows us to do calculation considering only the exchange of the many electron character as given by Slater, which shows this variation of Exc with respect to density being proportional to the 1/3 of the density. If electrons are interacting only through Pauli exclusion principle, we can adopt the exchange potential as derived above. One needs to remember these are not true electron wave function, but they gives rise to exactly the same density as true electrons. Since the density is the same, we can calculate from the energy functional the total energy of this system, although one is using not the true electron wave functions. But we know that electrons are not interacting merely through exclusion principle. They also experience the long-range Coulomb repulsion from each other. A part of this is already included in the Coulomb term or the Hartree term, which is given by E square integral of rho r prime divided by r minus r prime integrated over dr prime. The electrons themselves, being the interacting particles, experience the effect of this long-range interaction in the sense that motion of one affects the motion of each and every other one. This is known as correlation aspect of the many electron wave function. There has been various attempts to build the functional taking into account the correlation aspect in addition to exchange, which we are going to elaborate in the next slide. The table shown in this slide shows the various forms of approximations to the exchange correlation. The characteristic length associated with an n-electron system with density here in the following, will use this notation, is given by R inverse, which is related to rho to the power 1/3, and AB here is the Bohr radius. The leftmost column of the table gives the model, the middle and the rightmost column gives the exchange energy functional and the exchange correlation potential. In the exchange model, since the correlation is not considered, the correlation energy functional is set to 0 and exchange correlation potential is given by 4/3 epsilon x. In the model of Slater, the correlation energy functional is given by 3/2 alpha minus 1 times epsilon to the power x, while the exchange correlation potential is given by 2 alpha epsilon x. This is also therefore known as x alpha method, where alpha is normally chosen close to 1. Alpha is known as a first factor and typical choice of alpha is 0.7. In the approximation of the exchange correlation functional given by Wigner, the form of the exchange correlation functional is given in the following, where the values of the coefficient A and B are set to 0.884 and 7.8 respectively, and this is obtained by interpolation between known limits. In the model given by Hedin and Lindquist, the form of the exchange correlation potential is given by this complicated form with the specific choices and the values of the coefficients A and B, which is obtained by fitting to energy of uniform electron gas calculated by numerical methods at different densities. The model given by Perdue and Zunger has this form, which takes two different forms depending on whether Rs is less than 1 or Rs is greater than equal to 1, with the specific values of the coefficients A1, A2, A3 and A4 and that of B1, B2 and B3. This is similar in spirit to that given by Hedin and Lindquist, but uses sophisticated quantum Monte Carlo calculations done by Saperly and Adler. The common feature in all of the above approximations is that the exchange correlation energy EXC depends on density in a local fashion. This approximation is known as the local density approximation or LDA to the density functional theory. It consists of replacing the exchange correlation energy EXC by this integral which is integral over dr rho r e epsilon xc, that is a functional of rho r. So this epsilon xc is the exchange correlation density of a homogeneous electron gas having the same density as that of the true system. The effective potential thus depends only on local density, which becomes a local potential. As a result, it becomes much easier to solve than the Hartree-Fock equation with non-local exchange potential. At the same time, it goes beyond the independent electron approximation because of the correlation effect which is contained in Vxc. For the spin polarized case, the corresponding approximation is known as local spin density approximation, abbreviated as LSDA, is given by this following expression, where this V exchange correlation now depends on the suffix sigma, which is the suffix corresponding to the spin index, and here it depends separately on this two quantity, which is the charge density rho up and rho down, which are the charge densities in the down and up spin channels. Correspondingly, the epsilon xc also depends on this rho down and rho up. LDA is, however, a serious approximation. Even at the exchange level, the functional should be non-local. That is, it should depend on both R and R prime and rho R and R prime. LDA is expected to hold good when the density varies sufficiently slowly in space. That is, which is given by this following inequality, which is expressed as Kf inverse modulus over delta rho by rho much less than 1, where Kf is the Fermi wave function. This is, however, very often not satisfied, as is shown schematically in this following figure, considering the exact charge density for bulk copper. As you can see, this is hardly anything which is slowly varying. LDA, however, is found to be highly successful in describing the cohesive properties in most cases. The question naturally arises, why then LDA works in most cases? The exchange correlation energy functional, as was derived in the previous lecture, is given by the following expression, where, if you remember, this term f is the pair correlation function also introduced in the previous lecture. And rho times f minus 1 is the depletion in density due to exchange correlation hole around an electron at position r. LDA is the approximation in which the exact density depletion around an electron at position r is replaced by that of a homogeneous electron gas of density given by rho r, that is by the following expression as is shown in the following. The expression for the LDA is given in the right hand side. So you replace this depletion by this following expression in the LDA. The density depletion due to the exchange correlation hole around an electron corresponds to exactly 1. We thus have the sum rule, which is given by the following. You take this depletion in density and you integrate it over dr prime. That should give me exactly minus 1. This sum rule continues to hold also within the LDA approximation. Introducing the relative coordinate given by capital R, which is equal to r minus r prime, we have the following expression for the E exchange correlation, which is given by E squared by 2 integrated over dr rho r integrated over d capital R, R inverse times rho exchange correlation, where this rho exchange correlation, now it depends on this vector r and just the magnitude of capital R, because this is integrated over the theta and phi corresponding to capital R. It is given by this following expression. Note, because we have done the integration over theta and phi corresponding to that of the capital R, only the spherically symmetric part of the exchange correlation hole enters into the computation. Consider this integral, which is given here, which is d capital R rho exchange correlation over capital R. This is equal to nothing but the average of minus of average of inverse of R. This describes the inverse extension of this exchange correlation hole. If this inverse extension is approximated correctly, the LDA is expected then to work well. As clearly understood, the above, which was discussed in the previous slide, is a much easy condition to meet than the requirement of a slowly varying density, which we discussed previously. The angular average of exchange correlation hole density, which is the quantity that enters in the exchange correlation energy, EXC, is reproduced rather well as is shown in the figure by plotting the quantity given by LDA compared with the exact value, and this explains the origin of the success of LDA. Also, there is possible cancellation of errors between the exchange and the correlation part. We now discuss the generalized gradient approximation, which is abbreviated as GGA. A concentrated effort has been directed towards producing expression for this E exchange correlation going beyond LDA. One of the important class of such approximation is that of generalized gradient approximation. In generalized gradient approximation, or GGA, the functional depends both on the density as well as on its gradient. These days, one can use the GGA functionals introduced by Pardue and Wang, goes with the name abbreviation like PW, or by Pardue, Burke, and Erenzoff goes with the name as PBE, and also using Baker's formula for the exchange part combined with Pardue's 1986 formula for correlation. Substituting for the latter, that means for the correlation part, the formula of Lee, Wang, and Parr provides the so-called BYP-GGA or BLYP-GGA. The exchange correlation potential in this case in Cartesian coordinates is given by this following expression, which depends both on the first and the second radial derivatives of the density. It is an open issue whether to perform one of these GGAs over another. Depending on the application, they may yield somewhat differing result. One therefore needs to actually try various forms of this GGA and compare the results. However, the actual choice among these GGAs is usually less important than the difference between the LDA and the GGA themselves. The salient aspects of density functional theory can be summarized as following. Density functional theory is a single electron approximation theory where we did not neglect the exchange and correlation effects between electrons. We simply took them into account in an average way. This is the mean field approximation for the electron-electron interaction. It is an appropriate description where the effects of exchange and correlation are not crucial for describing the phenomena we are interested in. For example, all properties of solids that have to do with cohesion, they are generally described very reliably within density functional theory. Now, the natural question that arises, in spite of the drastic approximation of the single electron theory, why density functional theory is so successful? The general arguments that are given are the following. First of all is the variational principle. Due to the use of variational principle, the calculated density functional theory total energies are generally very good. Energy differences between the states of the system, which corresponds to different atomic configurations for which single electron equations are solved self-consistently each time, turn out to be extremely good. It, however, may fail in describing the case of coherent many-body states involving much more delicate phenomena in solids like superconductivity. As an example, the phenomena of superconductivity, as we just mentioned, involves energy scales of a few degrees of Kelvin, while the motion of atoms in solids involves energies of the order of 1 electron volt, which is 11,604 Kelvin. The second argument which works in favor of density functional theory and its success is the exclusion principle. To calculate the energy, the single electron states are filled up to the Fermi level, satisfying the Pauli exclusion principle. These are the optimal states as far as the energy is concerned within single electron picture. For a more accurate description, one needs to consider virtual excitations of this ground state. The correction to total energy involves the effect of excitations through the Coulomb interaction. These interactions, however, involve a pair of electrons or particles. The lowest order non-vanishing terms in the correction must involve, as we mentioned, the excitation of two electrons with energies EI and EJ which should be greater than EF, where EF is the Fermi velocity, and that of the two holes with energy En and Em, which should be less or equal to EF. The contribution of such excitations to the total energy is given by delta E, which is given by the modulus of this matrix element between phi I, phi j and phi n, phi m of this Coulomb potential, divided by this energy denominator given by EI plus EJ minus EM minus EN. However, the single particle states are orthogonal, so that there is no overlap between such states, giving rise to the product of phi I, phi m or phi j, phi n to be 0, except when I is equal to m, j is equal to n, or I is equal to n and j is equal to m. But these later cases, they do not correspond to an excitation at all. This indicates the corresponding corrections to the energy, which is given by this delta E, are very small. Thus, the energy of the system is reasonably well described by density functional theory already, and corrections to it tend to be small. The last argument that works in favor of density functional theory is that of the screening effect. The Coulomb interaction between real electrons is screened by the correlated motion of all other electrons. Each electron is surrounded by a region where the density of electronic charge is depleted, which we referred as the exchange correlation hole. This forms an effective positive charge cloud that screens an electron from all its neighbors. The net effect is a weakened interaction between electrons, therefore bringing the situation closer to the picture of non-interacting single electron. These particles, however, cannot be identified with individual electrons, as they carry with them the effect of interaction with other electrons in terms of the association with this exchange correlation hole. Therefore, not only the energies or the total energies are good, but the descriptions of the electronic behavior given by density functional theory are often found to be also very reasonable. In the following, we list some of the recent advances of density functional theory. Density functional theory has been extended also to the excited states as well as to handle time-dependent situations via the time-dependent density functional theory. While in the ground state density functional theory, the basic variable is the electron density given by this rho as a function of r, for a time-dependent situation, the corresponding quantity, that is the time-dependent density, which is now function of both r and t, together with the single electron current density given by J, which is function of R and T, form the basis. The second major advancement in the density functional theory is the inclusion of effect of finite temperature through the ab initio molecular dynamics simulation, which often is referred as AIMD simulations. To summarize, in this lecture, we started with Weinberg-Kohn-Sham formalism. As discussed, the crux of the problem lies in exchange correlation functional, which needs to be approximated. The local density approximation to the exchange correlation functional has been discussed at length. We also argued why local density approximation works so well. We also touched upon other approximation to exchange correlation functional, namely the generalized gradient approximation. Finally, the plausible reasons for the success of density functional theory has been discussed.